Discuss the basics of neural networks, understanding the importance of back propagation, and also looking at how neural networks brought about a paradigm change in which we didn't need to handcraft features. Now we'll discuss multi-layer perceptron, or the simplest forms of neural networks that we'll probably see. We'll start off with a one-layer perceptron, and we'll also understand what do we mean by the term layer. So we start off with the input, and this input is, in the case of perceptrons, we were having binary inputs, but now we are not restricted to that. These could be your input features, and we, for the purposes of consistency, we call this input as the input layer, and we finally have the output. So this could be a real number that you're trying to predict, or it could be a binary, or sorry, it could be a classification problem where this could be, let's say, the probability of the output being in a specific particular class. And then we have something known as a hidden layer. So what is not input and what is not output is known as a hidden layer. And in this case, we see that each of the input or each of the node in the preceding layer is connected to each of the node in the next layer. So this is an example of a fully connected neural network. And in this case, we just have one layer. So one layer means one hidden layer, right? And if you see that all of the neurons have the same structure, basically the same structure, which consists of two components, the first being a summation term and the second being an activation term. The idea of multi-layer perceptron is fairly simple. You're trying to learn even more complex decision functions, add more non-linearity to the network, and instead of the one hidden layer that you had previously, now you can have multiple hidden layers. In this example, I have shown two hidden layers. So this is where the term multi-layer perceptron comes into play. Now we'll be looking at some of the convention that we'll be following in this series of lectures, and based on after understanding this convention, we'll also do what is known as the forward pass of predicting from a neural network once we already have learned the parameters. So I'll be calling these different layers as layer 0, 1, 2, and 3. The input layer is by convention called layer 0, and the output layer, and then in this case we have two hidden layers going from 1 to 2, and finally we have an output layer. Now I'll be using some terms here, Z and A. These are the same meaning as we discussed earlier. Z is the summation term and A is the activation component of the neuron. Let's zoom in a little bit into the first neuron in the first layer. So layer 1, the first neuron over there. The first term is called Z square bracket 1, which is in the superscript, and subscript 1. So here the square bracket refers to the layer number, and we are currently in layer 1. So thus all of the neurons in this particular layer have the square bracket 1 as the superscript, and the subscript, which does not have any parenthesis or any bracket around it, tells us about the node number or the neuron number in that specific layer. So Z square bracket 1 and subscript 1 means the summation of the neuron, which that particular neuron belongs to layer 1 and is the node 1 or neuron 1 in that particular layer. Similarly, we have for the second neuron in this particular layer 1, it is going to be written by convention as Z superscript square bracket 1 and subscript 2, which tells layer 1 and node 2. Similarly, corresponding to each Z, we have an activation A, which uses the same convention. So thus the activation of the first node in layer 1 is A superscript 1 subscript 1, A superscript square bracket 1, sorry. Let's say if we look at hidden layer 2 and we look at its activation. So the The superscript is going to be square bracket 2 because it is in layer number 2, and the subscript is 2 because this is the second node in layer 2. So I'd request you to just pause at this moment, and just try and work through and understand and confirm that you are able to understand this convention well, because this is going to be the basis of the forward path that we're going to take. And finally, in layer 3, we'll, in this case, in particular example, we calculate the summation term is Z superscript square bracket 3 because this is the layer number 3, and since we have only one node, so the subscript is just 1. Correspondingly, we have A superscript square bracket 3 and subscript 1, which is also our y hat. Because we can write y hat as A superscript square bracket 3 and subscript 1, which is our output. Now, we also try to make things more general, and thus far, if you see from each of the layers, starting from layer 1 to layer last layer, the output is fed into the input of the next layer, right? And the output from this current layer is represented as A of square bracket 1, so on and so forth, or A square bracket subscript A of superscript square bracket L for the Lth layer. So just extending that convention even to the input layer, instead of just writing that as x1 through x small d, given a d-dimensional feature, we can also write this as A square bracket 0, 1 through subscript 1 through d, which tells us that this is the 0th layer, the activation from the 0th layer, which is the same as our input, right? As such, there was no operation being done, no Z being done, and no activation being computed. But this just helps us to extend the convention and make it easier to do all of the computation. So thus, we can also write the input, which is x1 through xd, which is a vector in Rd, as A square bracket 0 subscript 1 through A square bracket 0 subscript d, or which is a d by 1 dimensional vector now, right? Okay, now we're going to discuss about forward propagation. So I'm going to say that we have now associated with each of the edge here, there is some weight. And we also previously saw that we have a summation wi xi plus b kind of a format. And then we apply an activation on top of that, right? So let's just consider a single neuron. From the previous example, I'm just considering the neuron which is in layer 1 and the first neuron over there. So if you see that this has inputs from D such nodes in the previous layer, and it has another additional input which is the bias term, right? And now we want to write Z in terms of the Z square bracket 1 subscript 1 in terms of the other parameters or the input parameters. So I can write this as 1 times green is showing the weight of the bias term. So I'm writing the bias term as 1 into B square bracket 1 subscript 1, where B square bracket 1 indicates it is a bias term in the first layer, and subscript 1 indicates it's the bias term associated with the first node in layer 1, right? Plus x1, which is this input, times W square bracket 1, which again tells us this is a weight corresponding to the first layer, and 1 comma 1. I'll come to what is this comma 1 means. Similarly, for the input x2, we write x2 into W square bracket 1. Again, square bracket 1 means layer 1 comma 2. Now, if you've already figured out that, and if we generalize this, if we just proceed this further, we'll write xd into W square bracket 1 comma d. So again, you see, so 1 comma 1 comma 2 till 1 comma d. This is of this format. The general weights that I'm mentioning here are of the format W square bracket L, where L indicates the layer number, and the subscript is A comma B, where A means the Ath node in the Lth layer. So in this case, um, we are looking at node number 1, thus the term before the comma in this wait term is always 1, and A comma B. So B is the bth component of the previous layer activation. So since the previous layer was d-dimensional, thus we have the term after the comma going from 1 through small d. Right, so we can write z square bracket 1 subscript 1 in this particular fashion. Now let's introduce the convention back again. We said that we can write the input layer in form of the activation for the 0th layer, right? So we can write a square bracket 0. It's a d-dimensional vector. It's also the input, and I'm going to write these colored things, which indicate the weight going into the first node, as the weights for layer number 1 for the first node. So W square bracket 1 subscript 1 means weights for layer 1 node 1, and since the input is d-dimensional, these weights vector will also be a d-dimensional vector, right? And now I'm just going to write this in a more convenient fashion instead of having to expand this always. I'm going to write Z. One thing to note here is we've thus far dealing with all small case quantities, which means we're dealing with vectors thus far. We're not dealing with matrices, and when we deal with matrices, we'll be using capital letters. So this is small z. Z square bracket 1 subscript 1 is, by the way, a scalar quantity. So you should remember this is a scalar quantity, and we can obtain this by W square bracket 1 subscript 1 transpose times A0, or sorry, dot product with, or sorry, times A0 matrix multiplication plus P square bracket 1 subscript 1. So if you do it this particular way, if you can write the expression in this way, it's a convenient way to calculate the summation term that you're getting, or the summation Wixi plus Bi term for each of the node and each of the layer. We can write it in this particular fashion. And once we've calculated the summation, which is the z term, we can fairly quickly then also calculate the corresponding activation. And if you remember, the activation for node 1 and layer number 1 is A square bracket 1 subscript 1. And we can write this as the activation function G upon the input Z square bracket 1 subscript 1. Since Z square bracket 1 subscript 1 is the real number, then so is A square bracket 1 subscript 1. Right. Again, I would urge you to pause at this time and try to work through all of the convention that we have done thus far, because it only gets more involved from now on. Assuming you have done that, I'll move forward now. Okay, let's try and now work out the same logic for different examples for all of the nodes in this particular layer 1, hidden layer 1. So we can write A square bracket 1 subscript 1 as the activation function G applied on W square bracket 1 subscript 1 transpose A square bracket 0 plus B square bracket 1 subscript 1, and we can write the same formula for the other nodes in this network. So the other nodes, the second node in this layer is A square bracket 1 subscript 2 and A square bracket 1 subscript 3, and we can write this in fairly similar format. If you see, the only thing which is going to change is the set of weights and the bias. So the only thing which is constant, in fact, is just the input A0, and what is changing across each of these nodes is the weight vector and the bias scalar in this case, right? So we can now try and vectorize things a little. So whenever you've used TensorFlow or Keras or NumPy or even similar things like PyTorch, you probably deal with only vectors and matrices. You don't write multiple for loops. The idea is to make the computation more vectorized within and more efficiently calculable. So we are also now going to try and vectorize this whole computation. Instead of computing three things, instead of computing three scalars, can we directly compute a vector which is three-dimensional? And this will help us to do calculations faster. So we have thus far written these three quantities. We have z square bracket 1 subscript 1, z square bracket 1 subscript 2, and z square bracket 1 subscript 3. Now, the idea is, can we just stack up these three scalars and get a vector? And that's essentially what we are going to do. Now, let's take a very trivial example. I'll just put in some of the dimensions to help you understand this better. I'll assume for now that the input is three-dimensional. So we only have x1, x2, x3, or d is 3. And the bias term, as you would have seen corresponding to each neuron, is just a scalar. So it's a 1 by 1 quantity. The output we have already seen as I've said as a scalar, the output before you compute the activation, the z values. And so since you have three inputs, three-dimensional input, the weight vector will correspondingly be a 3 cross 1 vector. But if we take a transpose of that as we do here, we'll get a 1 cross 3 matrix, right? So you now have three 1 cross 1 scalar quantities and in the form of z's, and again three 1 cross 1 quantities, scalar quantities in the form of b's. A0 is multiplied is repeated across all of these three computations, and we also then have w square bracket 1 subscript 1, w square bracket 1 subscript 2, and so on and so forth. So I essentially write this as z square bracket 1. I drop the subscript now, which means that I've considered all the rows, all the nodes in that particular layer. And this can be efficiently written as a multiplication of a 3 cross 3 matrix with A0. A0 is a 3 cross 1 matrix, right? This 3 cross 3 matrix is now just stacking up w square bracket 1 transpose. Okay, let me repeat. W square bracket 1 subscript 1 the whole transpose, and w square bracket 1 subscript 2 the transpose, w square bracket 1 subscript 3 transpose. You write them across three different rows, you get a 3 cross 3 matrix. And you can also then verify the shapes. So you have a 3 cross 1 output, which you obtain by 3 cross 3 multiplied by 3 cross 1 plus a 3 cross 1. Right? So this way we can more efficiently do the computation for forward pass or forward propagation. Again, stop here. I would urge you to stop here, confirm that you've well understood this concept, because we'll be now assuming that you have understood this concept and take this further from here. So I'll be writing this matrix, which consists of w square bracket 1 subscript 1 transpose, etc., etc. I'll be writing this entire matrix, this matrix that you're seeing here, as a matrix capital W square bracket 1. So capital W now means we have started using a matrix now, and the square bracket 1, as you would expected, indicates that we're talking about the weight matrix for layer number 1. The other quantities are still vectors. So you have a z vector, and you have a z square bracket 1 vector and a b square bracket 1 vector, which indicates the bias, which indicates the summations and the corresponding activation vectors for layer number 1. Right? And then correspondingly, you can compute a simple function element-wise. So you now apply the activation function element-wise on z of 1. And then you'll correspondingly get a square bracket 1, which is now in this, the example that we're taking is a vector of dimension 3 cross 1. Okay, let's now take the computation further. Now we have obtained a square bracket 1 subscript 1, so on and so forth. In fact, we've just obtained the whole vector, which is a square bracket 1, which is now a three-dimensional vector because we have three nodes in layer number 1, right? We are trying to do the same calculation for layer number 2, so we can just vectorially write that z square bracket 2 is equal to w, capital W square bracket 2 multiplied by a square bracket 1, which is, if you've seen, it's a 3 cross 1 matrix or a three-dimensional vector, plus the bias term, the bias vector for layer number 2, which is now two-dimensional because we have two nodes in layer number 2. So a question for you, and then correspondingly also calculate a square bracket 2, which you would have figured out by now is again a two-dimensional vector because we have two outputs or two nodes in layer number 2. So question for you at this point is that what is the dimension of this weight matrix W, capital W square bracket 2? And this will also help you to better understand and grasp the subject and link whatever numbers we were computing and what we see graphically. Okay, so W, capital W square bracket 2, if you remember how we defined capital W square bracket 1, is to write, this is what you need to see, is to write the corresponding weights associated with each of the weights associated with each node in as a row, right? So the first row is the weights associated between all of the previous inputs and the corresponding node in layer 2. So we'll have weights coming in from layer 1 node 1 to layer 2 node 1, layer 1 node 2 to layer 2 node 1, and layer 1 node 3 to layer 2 node 1. So you have three inputs, right? So this particular thing is three elements. W square bracket 2 subscript 1 is three elements, and W square bracket 2 contains now two rows corresponding to the weights coming into the first node and the weights coming into the second node. So we have two such rows. Thus, the dimensionality of W square bracket 2 is R2 cross 3. Right? So now you would have already figured out that the dimensionality of the weight matrix of any layer is of the layer 2 was the number of nodes in layer 2 times the number of nodes in layer preceding layer. And then finally we can do the computation for the output layer, which is y hat can be computed as a square bracket 3 subscript 1, and which is g of z square bracket 3 subscript 1, or just g of z of square bracket 3, where z of square bracket 3 can be written as capital W square bracket 3, which is the weight matrix for layer 3, multiplied by a square bracket 2, which is the activations from layer 2, which is a two-dimensional vector, plus the biases coming into the biases for layer 3, which in this case is just a scalar because we have a single element, right? So let's now talk about the shapes of these different entities. which we have thus far seen through some examples, but we can just make things a little more formal now. So starting off with layer 0, which is the input layer, we said that we can write x1 through xd also as a square bracket 0, which means the activation of 0th layer. And I'm going to call n, capital N, square bracket 0 as the number of units in the 0th layer. So in general, capital N square bracket L tells us the number of units or number of neurons in the Lth layer, right? And we've already seen that we can write capital W square bracket 1 as the weight matrix for layer 1, and this is going to be now of the shape R capital N square bracket 1 times capital N square bracket 0. So basically the number of layers, number of neurons in layer 1 times the number of neurons in layer 0. That's the shape of the matrix, weight matrix corresponding to layer 1. And the bias term is simply you have a bias element for each of the node in a particular layer. So that will be of the dimension of the number of elements in that particular layer. So that's just, it's a n square bracket 1 dimensional vector, right? So if we are to summarize the shapes for all of the parameters that we have seen thus far, I'll firstly introduce or just reintroduce this convention. Capital N square bracket L means the number of nodes in the Lth layer. The first layer is the input layer, is the 0th layer, and that can be written as a square bracket 0, which is of the shape, which is an n0 shape vector. We can calculate, so we have a WL dimensional or WL shaped. So we have the weight vector associated with the Lth layer as capital W square bracket L, which is of the shape NL times NL minus 1. So number of neurons in the Lth layer times the number of neurons in the previous layer. The bias for the Lth layer is just the number of neurons in the Lth layer. And we can calculate Z of L as the summations or the summation vector corresponding to the number of neurons in the Lth layer. So thus it is equal to the number of neurons in the Lth layer, and similarly is the activation from the Lth layer. It's equal to the number of neurons in the Lth layer. Okay, I'll now quickly do an example of trying to solve MLP using a 2-layer perceptron, and I'll be using ReLU as the activation function. So these are some of the weights given. I'll just take a pause, in fact, and I'll come revisit this example in the next video.